Okay, these are the work problems for Chapter 6. Take a second to read it. First thing we need to do is draw our box. And I'm going to say there's my ground. And I'm going to push this box, apply some force to it. And at the end of the day, this box is going to end up over here. This is actually, 7 seconds according to that guy. And what I'm looking for is the net work done on this box. And I know that the net work is going to be equal to the net force multiplied by the distance that I pushed this box. Now, I can go ahead and I can calculate this force fairly quickly. I can say this box was accelerated at a rate of 2 meters per second, and I know what the mass is. So if I write Newton's second law, sum of forces is equal to the mass of the box multiplied by the acceleration of the box. The only force acting on that box was my force F right there. I know that the mass was 4 kilograms. I know the acceleration was 2 meters per second squared. So I can go ahead and calculate 8 newtons was equal to my force right there. That's how much force I applied to accelerate this box over those 7 seconds. So now I go back and I take a look at my work expression, and you immediately realize that I left a term out. I left out the cosine of the angle term. And in this case, my distance is going to be that distance right there. So the angle between my force and my distance is going to be 0, and cosine of 0 is going to give me 1, or unity. So I was, correct in writing work is equal to force times distance, but don't get into the habit of doing that because the angles might not always line up. So now I'm looking for, what is my distance right here. To do that, I need to go back to my old kinematics equations and say, okay, we got to set this guy up like a kinematics equation where this is my initial position. I'm going to call that equal to 0. It was accelerated from rest, so I know that my initial velocity was equal to 0. And at the end of the day, it's going to have some final position. I'm going to call that x. And that x is actually also going to be my distance that I'm interested in. So distance is equal to position, which is going to be equal to initial position plus initial velocity multiplied by time plus 1/2 acceleration times squared. And let's see, my initial position, I chose that to be equal to 0. My initial velocity, it started from rest. So at the end of the day, my distance is going to be equal to 1/2. The acceleration was 2 meters per second squared. And this guy went for 7 seconds. Quantity squared. My distance is going to be 49 meters. See, the amount of work that was done on that box is going to be equal to 8 newtons multiplied by 49 meters, and that's going to work out to be 390 newton meters or joules. Okay, so let's take a look at number 37. Here we have some car that is traveling with some velocity of 85 kilometers per hour. Now, I expect everyone is very fluent at doing unit conversions now, so I'm going to go ahead and simply write this velocity in meters per second, which is 23.6 meters per second. And at some later time, this car is going to use a coiled spring to come to a stop, and so maybe at some later time this car has used this coiled spring to reach a complete stop. It has compressed the spring, the spring was initially here, and it has been compressed by this distance x right here. 2.2 meters is what it says. And I also know that the car has a mass of 1,200 kilograms. Now, if you see something like this, what immediately jumps out to you is this should be a conservation of energy problem, and I have two conservative forces. I have my kinetic energy and I have my potential energy, so I can say that my energy of my car when it's moving is going to be all kinetic energy. Here it is all potential energy. So I know that my energy must be a constant, so my kinetic plus my potential initially must be equal to my kinetic plus my potential final. So kinetic energy 1 plus potential energy 1 must be equal to kinetic energy 2 plus potential energy 2. Initially I had no potential energy, and at the end of the day it's brought to a rest. I have no kinetic energy. So what I'm left with is my kinetic energy initially of the car must be equal to my potential energy of the spring. So 1/2 mass velocity squared is equal to 1/2 k x squared. And what I'm really interested in is what is this spring constant, or spring stiffness constant, k. So this is what I'm interested in solving for. I know x, I know v, and I know m. So the first thing I do is I multiply both sides by 2, and those guys cancel out. Now I divide both sides by x squared, and I get my spring constant k is equal to the mass velocity squared divided by x squared. Go ahead and I start plugging all this stuff in. Got my 1,200 kilograms, and my velocity is going to be 23.6 meters per second. Square that quantity, and down to the bottom here I'm going to have 2.2 meters, quantity squared. Go ahead, and at the end of the day I come up with 1.4 times 10 to the 5th, and the units are actually going to work out to newtons per meter, which is encouraging because that is the unit that you would expect for the spring constants. Lastly, problem number 60. If we have a car, and this car is traveling at a steady 95 kilometer per hour, or we can go ahead and we can convert this guy to 26.3 meters per second, then what we're looking for is it takes the car 18 horsepower to maintain this steady speed. What must the average force exerted on the car be due to friction and air resistance? So what that's saying is you've got some force due to the engine, and you must have some force due to friction in the opposite direction. It says it's traveling at a steady 95 kilometers per hour, so we know that the sum of the forces must be equal to the mass times the acceleration. Acceleration is steady, or velocity is steady, so the acceleration is a big fat 0, and therefore we have the force of the engine minus the force of friction. So the force of the engine is equal to the force of friction. Now we know that the engine is generating a power of 18 horsepower, and 1 horsepower is 746 watts. So we get rid of those guys, and we end up with 13,428 watts. That's how much power the engine is putting out. And lastly, we know the relationship between power and force. So this is going to be the force of the engine multiplied by the velocity. This is also, power of the engine. But we know from Newton's second law that the force of friction and the force of the engine are the same. So let's go ahead and let's solve for the force of the engine. We know what the power is and we know what the velocity is. The force of the engine is going to be equal to the power of the car, or power of the engine, divided by how fast it is going. It's going to be 13,428 watts divided by 26.3 meters per second. And we're left with 510 newtons. That's the force of the engine, but that is also the force due to friction because the car is, again, not accelerating. So we've gone ahead and we've calculated a force of friction must be 510 newtons.